Hello everyone. We'll get started in a minute. Okay, maybe we can get started. Um, Good evening, everyone. And today we will be covering the topic of transformers, which is the heart of large language models. We have covered this topic once before, and we want to touch upon it again. The reason is that we believe that this is one of the most important concepts that students who are interested in the field of large language modeling should be aware of, and they should master this concept completely. So we have started to conduct standalone webinars on the topic of transformers itself. So in this webinar, you will understand the complete basics of a transformer. We are not assuming that you have any prior knowledge. If you do, then that's great. It will be like a revision session for you. But if you don't, just try to absorb the content with a free slate and make sure that you get a very thorough understanding. If you have any doubts as the session is going on, just feel free to post them in the chat. We'll be sharing the recording of this webinar with all of you. So with this brief introduction, let us get started. So first, let me just quickly discuss about what exactly is generative AI. So if you look at traditional AI, here I have shown a picture of cats on the left and dogs on the right. So typically, what happens is that we feed this training data to a machine or a model which trains itself based on this training data and eventually learns to distinguish between cat and a dog. So this is what traditional AI does. So later in the testing, if you provide the model with a completely new picture of a cat or a dog, it learns to distinguish it quite easily because it is able to identify the different features which are present in the image. Now, what happens is that in the regime of generative AI, you ask a question which is typically very different from either classification or regression. The main question that you are interested in is can we create a completely new image of a cat or a dog from this data? Now, this question is intrinsically way more complicated than the first question because here we have to generate or create a completely new face from scratch. And this is what makes this field very powerful, but at the same time, way more complex to understand. And here I have shown an example of how generative AI can create a completely new image, which was not present in the training data before. And we have seen a lot of applications. The primary example being ChatGPT when it came in the latter half of 2022, it blowed everyone's minds. But actually, in the background, research on GPTs had already started way back 2 3 years back. In fact, when the Transformers paper was released in 2017, that was when I believe this field of generative AI really took off. And from there, the research has been happening at a very rapid pace. And now we are at a stage where we are seeing a lot of applications of generative AI. And going down the line, we believe that the applications will go on increasing more and more. So now with generative AI, it allows you to create completely new data from scratch. ChatGPT started with text to text. Later, we moved on to text to image and text to 3D models. Now we can even do text to videos. So I want to show you some examples of some interesting generative AI applications, which I believe some of you might not be aware of. So I just want to motivate you just to give you an understanding of where we have reached in this field. So this is an example of an application called SciSpace. So typically what used to happen previously with PhD research scholars is that they used to uh, go to Google Scholar, type in the name of the field they want to do research in, try to read the paper, and form form a sort of a connection in their mind of how the papers are connected between each other. So literature review was a tedious process. It still is to some extent, but because of generative AI, we have actually made a lot of progress in this area as well. So this is an example of an application which is called SciSpace. What here you can do is that you have to just type the name of the field. So let's say I'm interested in how does AI impact space exploration. And what it does is that it creates the list of papers for me, and not just that, it creates the list of insights also. So what's happening here is that because of generative AI, we are able to have the power to read the document and then summarize the document in the form of these insights. And this was not possible 5 years before. We could not summarize an entire document and get a lot of insights from that document, which is incredibly useful for a researcher. Imagine typing Google Scholar about this and then seeing some random results, and then it takes a lot of time to select the best 10 papers. But here, SciSpace does that for you. It gives you the best 10 papers, and along with that, it also gives you a lot of insights into all of these papers. So it really helps you in your research journey. Another application which is very interesting is called connected papers. What it does is that, let's say, uh, you want to research a particular paper and you want to see what are the works which this paper has cited and what all other papers have cited this paper. So those two are two different things. So connected papers will provide you with sort of a map, and this map will help you understand what all different connections have emerged from this paper. It's a combination of, you can see at the top there are prior works, which means that works which this paper has cited, and derivative works, which means the papers which have cited that particular paper. And this information you don't get very easily from Google Scholar. It usually takes some time. So these are some wonderful applications in the research domain. There are many other applications as well. This is an application called Gamma AI, which allows you to create entire presentations from scratch just by giving a single prompt. You can create a full 8 to 10 pages of presentation. It's really wonderful. And then this is an example of Runway AI, which allows you to create videos from text or images. So on the left, you can see we have attached an image of a volcano, and on the right is the video which is created from that particular image. If people, if some of you have not tried this application, just try it out after this webinar is completed. It's a wonderful application of generative AI and how far we have reached. Actually, till the beginning of this year, this technology was not very powerful. Text to video was very much in its nascent stages, and this model was, I think, released quite recently, Gen 3 Alpha Turbo, and it's very good compared to Gen 2, which was free for all users. So this is also free. They have some limited number of credits, but you can actually try it out. Then there is this new company called Servam AI, which is brilliant. Their main mission is to make generative AI real for Bharat, which means that for people in India who are used to speaking in different vernacular languages, they do not have any generative AI application that is catered towards their needs, right? That is non-existent. But the people at Servam they want to make applications which are made specifically for a person in India. Let's say I'm living in some remote village, and I want a personalized AI tutor. Currently, you cannot use ChatGPT, firstly because it's not free, and second because it's not very good to understand the vernacular language, which in day-to-day conversations we have a very specific way of speaking. And I would ideally need an AI which understands that way of speaking and actually speaks back to me in the same way. So these people are actually building a lot of products. If you see their list of products, they have some wonderful products. I encourage all of you to try out some of them. They have made some short demos of a lot of different. So let's say there is this input text and you can generate speech in different voices. Then they have a product where you can translate from one language to the other, which is way better than Google Scholar. Because in Google Translate, what happens is that it makes errors a lot of times because it's not trained on conversational language, which we use. But Saras, which is the translate model of Sarvam, is very good. You can speak as if you are speaking with a friend and it will transcribe the audio perfectly. These are some of the wonderful applications of generative AI, and I just wanted to demonstrate how far this field has reached. Now, with these examples, I will stop sharing my screen, and Raj will explain the next part.
Yeah, so let me start sharing my screen. I hope the Canva is visible. So first, let me start covering about evolution of generative AI. The reason we decided to put this section in the presentation is for you to appreciate the times which we are living in right now. So the breakthroughs which we are using right now, such as ChatGPT, all of us should be aware of the history which has led to this so that we can appreciate it much more. Before moving any further, let us do a quick poll, which all of you can answer. So, Sahil, can you please put the link in the chat where the participants can go and answer the poll question?
Yeah, sure. mm, Raj, can you share the projector panel? It has the link and the QR.
Just a minute, let me do that. So, yeah, this is the projector panel. Is this the link?
Yeah,
Okay, so I'm going to share this link on the chat. Can everyone please try going to this link? Just want to see if you're able to see this set of questions on the screen. It's showing page not found. Okay.
mm,
Let's see.
uh, is this all
Yeah.
good?
Can you
Yeah,
put this second link
yeah.
with Sahil? This is working? Okay, so Sahil has shared one more link actually. I'm just sharing this over here.
mm,
This scan is working for most of the people.
So what is everyone scanning?
QR code.
Okay. Then can everyone scan this QR code which is on the screen right now? I think this might work.
You can directly go to pigeonhole.at and then just put the
Vizuara AI.
yes,
Okay,
just go to
the
pigeonhole.
link is working. Mostly everything is working. So I can see that there are 24 votes. I really encourage all of you to answer this because then we can later see how many of you got it correct. And then there will also be a leaderboard. So please participate. So I can see that there are 88 people in this call, and here we can see only 37 votes. So we have this QR code option here, and there is also a link for you to go to in the chat. Please do both of it so that in just a few seconds we are going to look at the solution now. So 45 votes have been received, 46, uh, 48. So okay, now I'm going to look at the admin panel and show you all the solution. So let's see. So this is the admin panel, and we can see that 56% have answered correctly that Eliza was the first chatbot. That's awesome. But 24% answered ENIAC conversationalist and Parry, and then 16.7% surprisingly answered Alice. We can also see the leaderboard if I click on next right now. And here we can see, let's see how many people. So there are 20 rankings here. And how many people have got it correct? About 30 people have got it correct. So all of you 30 people are right now rank number one. We'll have multiple polls throughout the session. And this will give you more chances to improve your rankings. So now let's move to the next part, which is the history of generative AI. And as was shown in the poll, the first generative AI which was demonstrated was called as the ELIZA chatbot. And this was released in the year 1966. Let me show you a brief demonstration of this. So here I'm selecting the English language.
Please tell me what's been bothering you.
So here the ELIZA app is asking, please tell me what's been bothering you. And then I'm saying that I want to learn Generative AI, can you help? Can you please help?
Why do you want to learn generative AI?
Then Eliza asks, why do you want to learn generative AI? So then I say, because I want a job.
What does wanting a job have to do with this discussion?
Then Eliza says, what does wanting a job have to do with this discussion? It's pretty bad, right? You can all try going to this link and interacting with Eliza. I'll just share the link right now. But remember, this was 1960s. So it was around 60 years back. So we are all very lucky to be right now living in an age where ChatGPT, I would say, is 100 or even 1,000 times better than this. But at that time, it was considered to be revolutionary. This was the first, I would say, advancement in large language processing. And now in 60 years, we have come so far. So let me first tell you what happened in these 60 years and how we have reached this ChatGPT stage right now. So the first thing which really became popular, as you all must have known, is the first wave of neural networks. We started around 1980s, 1970s, 1980s. And the problem with neural networks was that they are quite good for prediction tasks, right? But they don't capture memory. And to predict the next word in a sequence, which is what large language models do, you need to capture memory because you need to know what has come before because context is important. The current word is not enough. You need to know the context. You need to know what was in the previous sentence. You need to know what was in the sentence before that in order to predict the next word. So whatever model you have, you need that model to capture memory or history. And neural networks simply do not do that. So neural networks are not good enough. They cannot do language modeling tasks. But there were three other models which essentially led to the revolution in LLMs. The first was recurrent neural networks. It was invented in 1980s. And I would say this was one of the first models which was hugely successful in language modeling tasks such as predicting the next sentence, etc. Then came long short-term memory, which addressed some of the issues of recurrent neural networks. And then in 20 years came the Transformers paper, which is essentially the origin of GPT or ChatGPT, which we all use on a daily basis. So you all need to first appreciate what are recurrent neural networks, what are long short-term memory networks, at least at an intuitive level, so that when we come to transformers in this webinar, you really understand why they have become such a big deal. So I will try to now give you an intuition for what RNNs are, what long short-term memory networks, which are also called LSTMs are. So how many people in this call know about RNNs? Can you just say yes or no in the chat so that I'm aware of the level of your knowledge with respect to this field? Okay, so I'm assuming that people have heard of this or know a bit about this, and there are also quite a few people who don't know about RNNs. That's completely fine. So the main difference between a neural network and a recurrent neural network is that a recurrent neural network maintains a hidden layer. It maintains a hidden state. And this hidden layer captures information about previous inputs. You can think of this as the memory block. So I told you that neural networks don't capture memory, right? This hidden state allows recurrent neural networks to capture memory. And now we can come to poll number two. So you can go to the same link as before and let me actually, yeah. So now when you click on the same link as before, you should be able to see question number two. Can you just type it in the chat whether you are able to see this question? So Sridhar shared this link again. You can click on this link and then you will be taken to this page where yeah, I think here. So I can see that 22 votes have been received and about 50 participants. Please try to be as motivated and inspired to answer because these 90 minutes you can devote fully to understanding the subject. So how do RNN recurrence feedback loops help in language tasks? The first question is by processing words faster. The second is by increasing vocabulary size. Third is by allowing the model to remember previous information. And fourth is improving spelling accuracy. Just want to check your understanding of RNN before I actually explain this to you. So 54 votes, 52 votes. So let me show you the answer now. So here you can see that the correct answer was by allowing the model to remember previous information, and 94% of you have got it right. And okay, so voting ended, answers have been revealed, and now we can see the leaderboard also. So let's see how many people have actually got all the questions correct. Now 25 people have got all the questions correct. Uh, and as you all correctly answered, it is because of the memory retention that RNNs are actually so good. So let me try to explain this a bit more. Let's say you want to predict the stock price for the blue company on day number 10. To make this prediction, you need to have the data of all the previous days, right? You need to have data from day 1, day 2, up till day number 9. So we need the neural network to be flexible in terms of the fact that it needs to take into account the information of the previous days also. And RNNs can do this. The way RNNs do this is they have a feedback loop. And this is the major difference between neural networks and recurrent neural networks. Neural networks don't have this feedback loop. This feedback loop enables the RNNs to basically have sequential input values. So previous values, multiple previous values to make future predictions. But these feedback loops have a problem. When you want to use some input from way back, you need to chain multiple feedback loops together. And this leads to something called as a vanishing gradient problem, which means that it becomes very difficult to train the recurrent neural network. And that was one of the major limitations of recurrent neural network, this vanishing gradient problem. So that essentially stops the learning of the RNN. It was awesome for a while, and RNNs really revolutionized, I would say, the language field, and people don't pay enough respect to what RNNs did. But at that time, it was pretty revolutionary. Then in 1997 came the second model, which is long short-term memory. How many of you know about LSTM? Can you just say yes or no in the chat? LSTM is a bit more niche, I would say, than RNN. So people would have heard of RNNs, but generally, very few people really know how a long short-term memory network really works. So the difference between RNN and LSTM is that LSTM actually uses two separate paths to make predictions about what happens tomorrow. It has one path which is for long-term memories, so memories which come long back, and it has one path for short-term memories, which is immediately accessible memories. And then it uses both these paths together to make the next prediction. So in the model, you see there is a line which runs at the top, which is the long-term memory. There is a line which runs in the middle, which is the hidden state for short-term memory. And both of these long and short-term memories actually combine to help the LSTM make the prediction about what comes next. I know I'm going a bit fast here, but I just want to give you an intuition of the fact that LSTMs have a long-term memory and a short-term memory, and they use both these to make the next prediction. And they were a significant improvement after recurrent neural networks. But that was not enough. Transformers entered the game in 2017, and there was a revolutionary paper which is called "Attention is All You Need." So this paper, which was published in 2017, I think it has more than 100,000 citations now. This really changed everything, and this paper introduced the transformer architecture, which is the path-breaking model which led to GPT later. So Sahil is going to cover the transformer part later. But before we come to transformers, we need to appreciate one thing which is very important. So all of us know that transformers do language tasks, right? We can give some input, then transformers basically, or GPT rather, understands the input and predicts the next word. Or transformers can also be used for language translation tasks. But the problem is that how would you give the input to the model? Because words cannot be understood by computers or models. They need to be converted into numerical representation. So before we understand the transformer model itself, first we need to understand the inputs to the transformer. So when we give sentences, the sentences are not directly processed by transformers. There is a process which is called as word embedding. So now we are going to understand a bit about word embedding. And before that, let me take a poll number 3 right now. So again, we will share this link in the chat for you all to answer the poll. Let me go to that link and find it. Yeah. So I've just shared it in the chat right now. You can go over here and answer the poll question. Let me also go over here. Yeah. So then the question is, what is the best way to represent words in the computer for use in the model? So the first is ASCII characters, the second is binary code, third is numerical representation, and fourth is image pixels. So remember, there are 25 people right now who are tied at the top position on the leaderboard. I assume that after this question, there will be fewer people, or maybe not. Let's see. So each time around 50 votes are being cast. So I guess only 50 people in the call are answering the question, but it's fine. Around 53 votes have been cast. So let's see. Now I'm going to go to the admin panel and I'm going to reveal the answer. So the answer is the best way to represent words in the computer for use in the model is numerical representation. So I can see that many people have been confused by binary code option. So around 20 votes have been cast for this option. Now let us actually look at the leaderboard. And now we can see that there were 25 people who were tied for the top spot initially, and now there are only 11. So 11 people in this call right now have got all the answers correct. So congrats to all of those. Others still have an option to rise up in the leaderboard if the top ones make a mistake. So please try to answer the next questions as accurately as possible. Okay, so let's come to vector embedding, right? So the main issue is that we have words, but computers cannot just understand words. We need numerical representation of words. So the question is, how can we represent words in numbers? So you might think, okay, just take all the words which come in the English language and assign random numbers to each word. So cat becomes 34, book becomes 2.9, tablet becomes -20, kitten becomes -13, etc. But the main issue with this is that if you look at cat and kitten, the meaning of these words are similar, right? Cat and kitten should be ideally related to each other. But if you use random numbers, these numbers don't capture anything about that relationship. So cat is 34 and kitten is -13. It says nothing about the fact that the words are semantically related to each other. So we cannot use random numbers. So let's go next. How many of you are aware of one hot encoding? Can you put it in the chat whether you are aware of the concept of one hot encoding or not? It's a pretty common machine learning concept. So I would say about 70 to 80% are aware. But basically what one hot encoding does is that you represent each word as a giant vector of zeros and only one element of that vector will be equal to 1. So you might say that, okay, let me do one hot encoding. So dog would be 0, 0, 0, 1, 0, 0, 0, let's say. Puppy puppy would be some different set of zeros and ones. Now the problem with this is that you can do one hot encoding for all the words, but again this does not capture any semantic meaning between words. Dog and puppy are related to each other, right? But if you do one hot encoding, it fails to capture the semantic relationship at all between these words. That's where the idea is born that what if you represent every word as a vector? So let's say I'm going to represent dog, cat, apple, and banana as 5-dimensional vector. So then you might ask, how do you make these 5 dimensions? So I say that, let's say the 5 dimensions are the features. So for the first dimension, I ask the question whether has a tail. The second dimension, I ask the question whether is eatable. The third dimension, I ask the question whether has 4 legs. Then I ask the question whether that word makes sound and whether is a pet. And then I'll make a vector for each word. So if you see now for the dog, the vector becomes 23, 2, 19, 12, and 35. For cat, it's 31, 3, 21, 18, and 31. Now, if you observe these two vectors closely, you will see that for has a tail, both of these have a higher value. For has 4 legs, both of these have higher value. For makes a sound and is a pet, both of these are higher value. So you will see that these vectors are related to each other. So these vectorized representations are actually capturing the semantic meaning of the words. Now, if you print out the vectors for apple and banana, and if you compare, let's say, dog and apple, you will see that they are completely different because apple has a very high value for is eatable and it has a very low value for other things like has 4 legs, etc. So dog and apple will be different. But if you now compare apple and banana, you will see that wherever apple is higher, banana is also higher. So these two vectors will be closer together because they are related to each other. That's when people got this idea that, oh wow, actually when numbers are represented as vectors, we can capture semantic relationship between them. That was an awesome idea. But then next came the question, how do you represent number as vectors, which also someone has asked in the chat. So this has to be done through a neural network training. So let's say you have a huge data set, right? And that data set consists of sentences from books, etc. So you know which words are related to which other words. So you train a giant neural network between the words and the vector embeddings which they should be having. And the hope is that when you train such a giant neural network, for each word, there will be vectors which are created and those vectors will capture the semantic meaning. For example, when you train on enough number of data, The vectors for dog and cat should be similar to each other. The vectors for apple and banana should be similar to each other. So for example, there is a Google News vector 300. There is an already trained word to vec Google News data set. So what here it has been done is that there 3 million words and phrases were taken for training. And then based on this training data, a giant neural network was trained to construct the mapping from words into vectors, into 300 dimensional vectors. And in fact, right now we are just going to see a Google Colab notebook. So I'm going to share this notebook also in the chat with you right now, and I'm going to conduct a hands-on demonstration of how vector embedding actually works. Um, so, okay, so I've shared this link in the chat. It might take you some time to download this, but you can also explore with it later after this session is over. So what I'm doing here is now I have imported the word to vec Google News model. So this is already pre-trained. So this model already can take in any word as an input and it can convert it into an embedding vector which captures the meaning. So I've loaded this model right now, and this 300 means that what this model will do is that it will convert all words into 300 dimension vectors. So it's a very hugely high dimensional space which we cannot even imagine. So now if you actually take this model and see the vector for the word computer, you will see that you get this vector and it has 300 dimensions. Awesome. You can even print the vector for the word cat and you'll see that it has the shape of 300. But what I really want to illustrate to you is this. So let's say if the vectors are indeed capturing the meaning, let us test this out. So let's say if you have a vector for king, and if you have a vector for woman, and if you have a vector for man. So if you add the vector for king to the vector for woman and subtract the vector for man, what should you ideally get? Can you all type it in the chat? What do you think should be the answer for this? Okay, so almost everyone is saying queen, because as humans, what we are intuitively doing is that we are adding a masculine aspect with a feminine aspect and subtracting another masculine aspect. So what should result is a feminine aspect. So that's why all of us say that, okay, woman and man is there, so king and queen should be there. But actually, it's pretty awesome that if you encode this king, woman, and man into vectors, and if you do this subtraction, let's see what we recover. So what I do is I add the vector for king and woman, and I subtract the vector for man, and then I print out the top 10 answers. So if you print this out, you will see that queen is the word which is uh, predicted with the most highest probability. So the model, the word to vec model is pretty confident that king plus woman minus man should result in a vector which has the meaning of queen. Isn't that amazing? This is a direct indication that we have actually captured the semantic meaning between words, which all of us humans already have that inbuilt knowledge. That's why vector embeddings really work. Earlier, I was pretty unsure that whether vectors can indeed capture the meaning. But this addition and subtraction actually is the perfect proof that vectors are indeed capturing the meaning of words. We can even do another check. So we can actually take vectors and find the similarity between the vectors. You can think of it as finding the distance between two vectors in a high dimensional space. So if I find the similarity between woman, man, king, queen, uncle, aunt, boy, girl, nephew, niece, you'll see that it's pretty high. But if you find the similarity between the vector for paper and water, it's pretty low. It's around 0.11. This again indicates that the vectors are capturing the meaning. Similarly, what we can do is that if you have vectors for all of these words, you can take the distance between the vectors to find how related they are. So to find how related man and woman are, I just take the distance between these two vectors. Similarly for semiconductor and earthworm, and similarly for nephew and niece. And if I print out these differences, I'll see that the magnitude of the vector difference between man and woman is 1.73. The magnitude of the vector difference between nephew and niece is 1.96. And the magnitude of vector difference between semiconductor and earthworm is pretty high. Why is this pretty high? Because semiconductor and earthworm are not related to each other at all. And that is actually being captured through vectors. That's awesome, right? We have essentially converted the mathematical difference into an intuitive sense of meaning. Semiconductor and earthworm are not related, so the vectors for these would be very much far apart. That's why the distance between them is pretty high. So what is done is that when we are going to come to transformers now in the next section, and when you look at these inputs, What are these inputs? These inputs are vectors for each words. So direct words or direct sentences are never given as inputs, but 300 dimension vectors or higher dimension vectors which capture the meaning of the words are given as inputs to these transformers. So please keep that in mind. Now we are going to move to the next section. And now I'll stop sharing screen here and Sahil will cover the next section on what exactly are transformers.
Yes, thank you, Raj. Hi, everyone. Let me just share my screen. Okay. Yep. Yeah. So you don't need to be intimidated by this figure. You might have also seen this figure in several places, but we'll try to understand what this actually means. And over here, it's a specific architecture. There are many variations of it. For example, in GPT, a slight variation of it is used, but the basic principles of the transformers remain the same. So just before going ahead, let me just take a poll. Can you all go to the poll again? It's a simple question. It's okay if you don't know the answer to this. It's just to know what were the problems introduced. Let me just. Okay. Yeah, I hope everybody can see the question.
Sahil, on your screen, the what is transformer slide is visible.
Okay. Let me just. And just go to pigeonhole .at. Okay. Just a second. I'll just share you the screen properly. Okay. Okay, so sorry, Arjun. Yeah, now we are back. Okay, here's the question. I think everybody had enough time to answer it. So let's just see the answer. Okay, the answer is machine translation. So it was initially introduced for machine translation. So, okay, we'll just take a look at the leaderboard also. Yeah, so far, like 6 people have got all 4 correct. Yeah. So initially, the transformers, when it was introduced in 2017, it was meant to only translate, like it was meant for machine translation. But later on, it gained some more traction, and people understood that just by having this model, which is capable of understanding language to an extent that it is able to translate it, it can be used for other things also. And that is why the new models, like even GPT, which is generative pre-trained transformers, and all of that came. So in the history, like we already talked about RNN, LSTM, all of these before, and this was back in 2014. And around 2016, 2017, when the transformer model was introduced, that followed with a series of other models like BERT, which is also used for translation. And there is GPT-3, GPT-4, and all of these models came, even T5, which is available online, even Google's Palm, all of these came from the transformer model. And all of these are based on the transformer model. In a way, you can say that it has revolutionized the NLP space. Okay, in this figure, what you can see is it is a bit complicated on the right side, but if you look over here, you can see that there is this encoder and a decoder block. So even if you're looking for a simple machine translation, we give a certain amount of input, like earlier Raj talked about, we give an input and then we feed it to the encoder. And there we get a middle representation in between. So from the encoder, what we get is an output, which is like a certain representation. You can think of this as an understanding. Let's say if you want to translate from English to Hindi or something like that, what we first do is we try to understand the language, which is said in English, right? The sentence. Let's say if it's something like how are you? And then you first try to understand what how are you is. And that is what the encoder does. It gives you a middle representation. And the decoder, what its job is, it takes whatever representation was learned by the model as the input. And then using that, it tries to generate what the output sentence is. So if it is in Hindi, it has to be ab kaise ho, something like that. And this is generated by the decoder. So sometimes in some models, we don't need the encoder, and sometimes we don't need the decoder. And just before that, okay, let's talk about this, that we feed this into the encoder block, and told you that we feed the input as we said in the previous slide, that but also along with that, we add some kind of a positional value to this. And this is because in RNNs, what we do is we just give the whole sentence as a sequence. But one of the main advantages of transformers is that you can just give all of that in parallel. So there is no order of when we feed all of it, we don't know where which word comes. Okay, let me just go to the poll again. It's not open. Right. Okay, this is the next question. Can you try to answer this? What is finally inputted to the transform block? Just to see that if you understood this exactly. I can see that there are 4 votes. Let me also look at the chat. Okay, I think reaches 50. I can reveal the answers. Okay, so most of you also gave the answer as word embeddings. That's okay. And also one hot encoded vectors. But the correct answer is the encoded input, which is in parallel. So let me go back here. So over here, the main difference I said from RNN is that we do not give all of the words in a sequence. We give it separately. So when we just give all of the words separately, we don't know which word comes first. And that is why in transformers, there is the additional thing which we add here, which is the positional encoding. We won't get too deep into how the positional encoding is done. There are several ways to do that. And one of it is like an absolute value, just add to the input so that you can know the first word is in a certain place. And sometimes in GPT or something, it's also learned. Let me go to the next slide. And you can see that there are several models like GPT-2 and BERT, and some of them use only the encoder architecture, and some of them has a decoder only architecture. So when you take something like GPT-2, what we have is a decoder only architecture. And this is because we don't need an input from another language or anything like a translation task. We just give a first word. Like you might have used ChatGPT, and then you just feed in one word, and then the model's job is to predict what the next word is. And here you can see this is the input we are giving, which is a numerical representation. So let's say we have a series of values, and each word will have several lines of data, right? And as in each word is represented by several numbers, as Raj said earlier, and that is the input. So this blue box you can see here is the transformer block, the first transformer block. So let's get into that. Okay, this is a visualization tool by Polo Club, and I'll be using this to give you a better idea, of a visual idea of how this works from start to the end. Don't worry about the right side of the screen. Let's start from the input embeddings here. So we have the input embeddings here. And as you can see, we first add a certain token embedding, as in we have a value or like a list of values. And what we do is we add the positional value to it, as in, okay, art comes first, this comes second, something like that. And you can see that even some words are split into two. That is also for convenience, because art appears a lot of times, and this happens in the tokenization or like converting words into numbers. Sometimes not entire words are converted, rather words are also divided into pieces. So this is taken, and then we have the functional and added, and then you get the first input. And if you look at the slide, you can see you get the embedding, and then it goes to the first transformer block. And what happens there is that now we have, let's say, these matrices, which is like 6 into 768. We're assuming that each of these words have like 768 rows. Okay, so art is represented by 768 rows. Visual is also represented by 768 rows, just like that. And there are 6, because there are 6 tokens in total. There is 3, 4, 5, 6 tokens. So the first thing what we do is we project it into a certain space. That means that we have this as like 6 into 768. What we do is we transform it into a different query key value space. We don't need to understand deeply about what query key value is. Just understand that it is transformed into a different space so that we can, let me just, okay. Yeah, so what we do is we do the same transformation. So we have 3 matrices now: query, key, and value, and these are learned. So what happens is, let me just show you what happens here. These values when taken, these matrices when taken, first what we do is we multiply the query with the key. And what we aim to do over here is that we are trying to find the relationship between all of these words. Okay, if I use some other example, let's say they discovered and if you generate, uh, we can see that there are some connections between, on the desert planet, they discovered a young. That means that a deserted planet has a lot of value in this sentence. What RNNs exactly fail to capture is how each of these words are related to each other. But what transformers succeed in doing is that it can see the relationship between all of these words rather than just blindly predicting what the next word is. It also captures all the relationship between all of these words. So first we take the dot product. That's just multiply all of these values together. And then how this is done, like what value is initially taken. Like we have, of course, the input here, and this key query and value. What kind of transformation is done here is completely learned by the model. It is one of the things which is learned by the model, in addition to what a normal neural network would be doing, which is just learning the weights of the model from the input to the output. It has hidden layers in between. It's just learning the values. It's just passing through it, and backpropagation is happening. Over here, these 3 are some additional weights which we learned. This is query, key, and value. And depending on the learned key, query, and value, we can, for example, if deserted planet needs to have some importance in the sentence, the query and the key matrices will be learned in such a way that it pays more attention, or it gives more importance. Or when you multiply, or when you do the dot product, the value for these become higher. So once we have that, we have it's also called the attention scores, as in which part of the sentence we should pay most attention to. So here you can see in a longer sentence, the animal didn't cross the street because it was too tired. You have it later coming on, but in an RNN model, it is very difficult for the model, that because the model is also too simple to understand what it means. It might be completely different, but in a transformer based model, it has the ability to pay attention to all of these tokens before. So what it would do is it probably point towards the animal. So if we take the attention scores over here, we can see that it has more connection towards the end animal, so that it has a better understanding of it. And once you have that, then you have another matrix, which is the value matrix, which we used to multiply it with whatever attention score we got, so that we get the output from this attention block. We'll see what happens to that output later. Before that, let me go over here. I'll also talk about this part where in a normal fully connected ear, this is a normal neural network. What you have, like we have an input and we have hidden layers in between, and then we have the output, right? So we have forward propagation happening, we have backward propagation happening. Over here, the only weights, the input is directly going through all of these weights. And the only thing which changes is like we'll say, okay, change this weight by a certain amount. And that is in effect back propagation. And we just see that, but we don't see change anything in between the connections between these layers. Even in a convolution, we maybe not all of you know about convolutional neural networks, but understand that it also does a similar thing where it just does a transformation, but it doesn't see how this transformation is done, or this is never changed. But in the case of attention, we have the ability to pay attention to each of these words separately, as in this case, in addition to just going through to the next layer. So in effect, a transformers also has all of these fully connected ears, just like a normal neural network, so that we are optimizing the neural network through backpropagation. But also it has this ability to learn the connection between all of these words. With that, let me just go to the next poll, if everybody can, right? Just go to the next question. Okay. I'll also check the chat while you all join the quiz. Okay, I can see 5, 7. Okay. Get to layer normalization. All right. There are 43 votes. I think I can end the poll, right? Give 5 more seconds. All right. It's okay if you don't know this yet, because I'm about to just get into it. And this is the correct answer by using multiple attention layers in parallel. So over here, like a single attention head, it might be able to pay attention to some of these words, and it might learn some particular feature of the language, which helps in predicting the next word. But we might not just need one thing. Let's say we need to know what, if it is a noun or not, if it is a verb or not, things like that too. And there are several complicated things which we need to learn, capture from the language, right? Not just the link between them. So one way to do this is using a multi-head attention. So if we go back over here, we can see that there are 12 attention heads in this particular model. And this is a GPT-2 model, by the way. If I had missed saying that, this is a example of a GPT-2 model. And you can see that there are 12 attention heads. And if you look at each of these attention heads, they would have a different attention metrics over here, as in they would be paying attention to different words because of different reasons. And these reasons are never exact. Like I gave an example that it might be detecting a certain noun or not, or a verb or not, but these are just speculations. So in effect, all of these 12 layers might also have some overlap, but they in effect learn all of these features. And once you have all of these 12 attention head outputs, okay, and just before that, I need to also get into masked attention here. And masked attention is something which is only there in the decoder. And I'll tell you why it is in the decoder. As you can see here, half of this is grayed out. And if you look at the attention metrics, you can see that if it's a simple sentence, life is short, eat dessert first. If this is the sentence, we have both of them as a column and the row, right? But when you're generating, we don't need the model to peek to future words. When you just have life, you don't need the model to peek to the next word. So when you have all of these words, it shouldn't peek. So that's why we just gray out all of these future tokens. So when you go to life, you don't have the next one. So only when you go to is that you get access to this is word also. So that is one thing which is in the decoder. So maybe in some other architecture, like a normal GPT architecture, where a normal transformer architecture, where you don't have a particular, where you don't have only a decoder network and you also have an encoder network, you can see that it only has a multi-head attention instead of a masked multi-head attention. We don't need to look into the encoder block right now. We'll just look at the decoder only architecture, which is a little bit more simpler. Right. Yeah, so the main purpose of this masking is so that you don't peek, the model doesn't peek into the future tokens, right? Okay. Let me just go to the next poll now. Just before going to the next poll, let me come here. And then you can also see that this is what is being outputted back into the neural network. You can just see the neural network as the input is going on the left and the output is on the right, right? And you can see something called the residual here. I want you to guess what this means. So if you can just go to the quiz link, which is here, you can go to pigeonhole.at and then put vizuara.ai. And if you can just guess what the answer to this is, like why would you need some sort of a residual connection? Just to recap, we have the input over here and we added all the embeddings and we fed into the attention, multi-head attention, because we have several attention layers, but we are giving it back to the model now and it is going from left to right. We have something here. And what do you think that is for? I'll just wait for you to answer. It's okay if you don't know this. And I'll tell you why it is. Okay, there are 42 participants and like around 30 words. Once it matches, I'll just... Right. Okay, I think I can go now. Let me just reveal the answer. Okay, it is to allow the information to flow directly from earlier layers to later layers. It's a bit confusing, I know. So the main thing is earlier Rast said that when we're using something like an RNN, there's a problem of a vanishing gradient. And this is because as the model gets a lot complicated, it's not really easy to just optimize the model just like that. Because when you do a lot of calculations in a row, like over here also we do a lot of calculations. And if you just feed in that output, what could possibly happen is that we lose the essence of the original information. Or like there are too many calculations happening that we don't know what is happening in exact. So a way which is from an earlier paper, residual neural networks or ResNets, we use that principle here. And what we do is we do a split here. So when we feed in the input, as you can, if you just look at the architecture over here, you can see that there is a bypass over here, right? So we feed the input to the mass multi-head attention and also bypass it. That means half of it is all of these attention outputs, and the other half is just the input, a piece of the input. And this keeps on happening at several places. The residual connection happens. This is so that this particular block, which we do this calculation, like the mass multi-head attention over here, it is very complex. It's a very complex layer. So we don't want to lose any information from the starting end so that all the gradients flow through easily. And you can see there are layer normalizations here and here. And somebody also asked what layer normalization means. A layer normalization is required so that if the values are in a different range, and over here to the output from the masked multi-head attention and the original input is being added together. So if all of these values just get added up and multiplied and all, it might be a huge value, or it might go to random values. So this layer normalization is introduced so that throughout the model, there is a certain range of values. Let's say if it's uh, between 0 to 1 or something like that, it stays in a particular value correctly throughout it. So if you do a lot of multiplications, you probably do want to do a normalization after that so that you can normalize the entire data. Okay. So even in this architecture, you can see that there are these residual connections, and this is within one particular model, one particular attention head too. As you can see from the input, it's split over here, it goes and it only joins over here. And here you have an MLP, or a multi-layer perceptron. An MLP is like uh, a simple neural network which just has a lot of which just have hidden layers in between, and it has all of these neurons which are also called as perceptrons. So you just add up. And this is a simple feed-forward network which you have here. And in effect, what happens is that we have the input and we have this going in parallel, and we have this feed-forward network here. And we got this output of what relations words have to each other from the attention. And we also extracted several features in the multi-head attention layer. And remember that this is just one block or one decoder block. If you see over here, you can see that there are several decoder blocks for the GPT-2 model. And in GPT-2, there are 12 models in the original implementation. But in several other models, like maybe GPT-3, they may have around 96 blocks. They could even have even more blocks than that, depending on the size of the model. You can even have even lesser than that. The original transformer model, they had just 6 encoder blocks and 6 decoder blocks. So yeah. So all of these 12 attention heads, all of those features we extracted. Now this MLP, its job is to make sense of whatever score we got. We might get all of these random numbers. So this MLP just gets really good at capturing all of this information. And even if you need to get a complex information from a sentence, or like from a PDF, let's say, and we have some semantic relations or some relations which we captured in the first layer, that might not be enough. We might need multiple levels, as in, okay, that we have a phone, and this phone is this particular model, and then later somebody dropped it, or like the screen shattered, or like the color is this. And when we say all of these, or like we make more additions to it, it has to be able to relate to all of these together. That means that it needs to create a more complex understanding. And that is what this does. This series of multi-head attention followed by a feed-forward network. And that is one. And then we have 12 of these stacked together. And once you go through that, we have a more complicated or a more complex understanding of whatever the input token was and how it relates to each other. Right. And once you have that, and you can see that there are more residual connections here, just like before. And you have 11 more identical transformer blocks which are coming here. And the final probability, the final output, what the model gives is just the probability. Like we have the vocabulary, right? Let's say we have the vocabulary of around 12,000 words initially. We're just going to predict what word comes next. And that is why it's called generative pre-trained transformer. Like its main goal is to just predict what word comes next. And all of these complications just aid it in generating that even more better. We could have a very simple statistical model. If we feed in a lot of data and then you check the occurrence of this sentence in the data corpus, or like a young male, if young male comes, or discovered a young male comes, what word comes next, right? You can just statistically generate it. But the issue there is that we won't have a more complex understanding of how all of these relate to each other. Or earlier, like I said, when it comes, it doesn't know what it is connected to the animal. Things like that would be difficult to understand with a simpler model. And this transformer model excels in doing that using this self-attention, multi-head attention mechanisms. And you can see here the final output with the probability of 3% is with, yeah. So when you're generating word by word, you first feed, okay, let me just track this. The first token which you would give is a start token. There are some special tokens too. We won't get into that in detail right now. We have several special tokens like stop. So how do you know when to stop? We just keep on generating. Let's say I generate the next word here. I keep on generating. And then when do you know when to stop, right? So sometimes the model generates the end of the sentence token, and then that's when the sentence ends. There are several special tokens like that. We won't get into that. But that's the first token which is passed here. And then you have A passed here, and you have the output. So what happens is this output is like a robot. Robot is the next word. And then this robot is fed back into the input. And now you can also see that the masked attention will also have access to the next word, right? And then you get the output from A and robot together, and you get the next output. And let me just, okay, save that for later. And just before that, you have seen that this gives an output. So how does it get to the probabilities, right? How do you just get the probability out of nowhere? Like we just having a neural network output. So the output we have here would be like logits, right? That means this is values. So what we do is we just do a softmax. If you don't know what a softmax is, what it does is it just gives you distribution, as in what word is more likely. So if it is close, something which is close to zero, it will drag it down to zero even more. And if it's close to one, it will drag it down to one even more. So it just normalizes the value between zero and one. It gives a distribution. So initially, when you do all the calculations over here, you might get large values, and we might not be able to directly give the output from that. So we just use the softmax just to normalize it. So first we do a 0 to 1 range, and we see that, okay, if you have 3% over here, that means that this has a chance of it being, okay, hair as 3%. Let me try some other example. Yeah. Yeah, so over here you can see that this coma is what is predicted with this. And you can see that the highest probability is 3.68, but somehow this is being selected. And this is because if we have a model like GPT-3, which is like a very complex model, and we force it to generate just one word, and it is like repeatable like that, it might not be really good at that. Like if we ask somebody these questions, if I ask you to fill this, everybody will have a different answer, right? So we need to somehow mimic that. So this temperature control, and that is the term which is used. This temperature, when it is very low, that means that the highest probability is just pushed ahead, and we just take that. So according to whatever the model learned, visualize is what is the most likely, and then it will just reduce all the other probabilities to less. So the model will just predict visualize. But if we increase the temperature, we can create some sort of an artificial randomness, and also give opportunity to more of the other words, which could also possibly be true. And without this, we might have very bad results. I haven't tried this out before, but let me just maybe try an example. If I just put the temperature as 0 and then generate 3 words, the importance of. So it is generating the over here, right? But if you have a different temperature instead of the, even though words like the has a very high frequency, and it almost fits anywhere, and it is very easy, so that the word the has a higher frequency. So in situations like this is also when we need temperature tuning, so that it generates a good value. We won't ever get the exact word we know, because there is nothing like the exact word which is supposed to be predicted next. But what we can do is we can create some sort of artificial randomness also here, so that we get a human-like input, human-like output, let's say. And all of these models in production, they have a preset temperature value, which is done by the developers. And some of them, we can also adjust the temperature values. And that is the final output we are going to get with the transform model. I think that is about it. So let's just to recap, we first give the input, we add all the partial values, we just put into query key values. The same word, like I goes to query key value, E also goes to query key value. That means that this is learned. What Q does to this matrix, it's like a matrix, and what it does to this word I is learned by the model. I mean, the value of that matrix, the Q metric, the Q weight matrix is learned. Q is also learned, and it is learned for all of these attention heads. And then you get and then you calculate the attention scores, you multiply it with the value matrix also. And this output, whatever is taken, we try to makes a sense of whatever value is being gotten here using the feed-forward networks. And we also have all of these residual networks so that we don't lose the gradient, or we don't lose a lot of information while we do all of these calculations. We repeat this around 12 times for GPT-2, and then the final output, we just get a softmax layer, and we give the log or the probabilities of what word comes next. Um, just before going to the next section, there'll be one more poll we'll do. Let's go here. Okay, this is rather a fun question. I am pretty sure like it's not easy to answer. You can take a good guess at it, and then this will make more sense once we go into the next section, like why this question was asked. I think, okay, there are 33 participants. You can take a good guess. I hope you're not Googling this. It's all right if you get this wrong. You can just try to get a good guess. Okay, there are 23 votes so far. Okay. I think it reaches 30. I'll just reveal the answers. All right. I'm just going to reveal the answers. Okay, it actually took 3 months on 10,000 NVIDIA V100 GPUs. And V100s are not cheap GPUs, they are very powerful GPUs. But still, it took around 3 months to train. But right now, today, we have simpler models, which are easier to train. There are small language models too. And also, right now, we have enough power and we have enough research in this field that we can also train models ourselves, which will be our next section, which will be like taken by Sridhar. And also, like, congratulations to Diligent Falcon, who somehow got 8 out of 8 right. If somebody asked these questions to me, I don't know if I would have got 8 out of 8 right. Congratulations to you. And yeah, I think a lot of people got 7 out of 8 right and 6 out of 8 right too. Yeah, it was great. Yeah. And congratulations to Diligent Falcon, whoever that is. I think you can reveal yourself in the chat later. I'll just hand over to Sridhar now.
Thanks, Sahil. Can you hear my voice all right?
Yeah.
Okay, awesome. So in this section, we'll be training a GPT by ourselves completely from scratch. And surprisingly, it won't take much time. It will take only a few minutes. So let me start sharing my screen. So I don't know how many of you have heard Andre Karpathy. He was a co-founder at OpenAI, and he worked there for a while before moving out. And he's a very, very big name in the AI community right now. So last year, he had actually posted a video on his own YouTube channel, which was called "Let's Build a GPT from Scratch." This is not an easy video. It's 2 hours long. It's very dense. It's difficult to follow, but surprisingly, it had almost 4.65 million views. So in this particular lecture, he introduced something called Nano GPT. So Nano GPT is nothing but something that he proposed, which is a very small version of an actual GPT. So in this link, I'll share the link to this particular website. You can go and see the actual visualization of GPT. So let's first look at Nano GPT. So Nano GPT is something like this. This guy has built, his name is Brian, I think. He has built this very beautiful looking animation showing the flow of input into position embedding, sorry, vector embedding, and then vector embedding into uh, later into the attention head, everything. So here he has uh, completely decomposed the whole process of predicting the next word step by step. So just go to this website. If later, you don't have to do it right now. Just go to this website, click Nano GPT, and see how this whole thing works. All you have to do is like click these play buttons. It will play the animation of the next step one by one. See, it's very, very cool. If you spend like maybe 1 hour on this, you will understand a lot about why some of these, attention head dimension is something by something. Why is it a square matrix? How do you project something onto a bigger space, bigger dimension space, and then project back down? All of these questions that you may have right now will be clarified. But what we are going to do today is he also published a GitHub repository. I'll share the link to this in the chat. Just look at the popularity of this repo. It has 36,000 stars, which is a big deal. Star is very different from likes in a social media post. It's very, very difficult even to get 1 star. This has huge number of stars. So what we have done is we can fork this repository so that you can have a copy of this repo yourself, and then you can work on top of it. So what I have done is I have created a copy of this in my own computer, and in that we will use uh, that particular code to train a Nano GPT ourselves. So Nano GPT is very small if you compare it with the size of GPT-3. So if I click here, you zoom out a lot. This whole thing is like a zoomed out view of all the different layers and all the different parameters in GPT-3. GPT-4, GPT-4o are even more complex. Here, if you look at Nano GPT, it's so small in comparison to see how much I'm zooming in. You can't even see Nano GPT here. See, if you see this small dot over here, that is Nano GPT. This whole huge thing is GPT-3. So it's very, very small. So the reason why Sahil asked how much time and how many GPUs did it take to train GPT-3, the question was asked because that time was huge, the resources were huge, the amount of money spent was probably in single-digit $1 million. And here on a normal computer, we can train it in a couple of minutes. So what I have done is I have copied a version of the Nano GPT GitHub repository on my own computer, and I'll open it. Okay, so this is the repo. So today what we are going to do is we will train the Nano GPT on a particular data set called Spotify Million Songs dataset. So this is there on Kaggle. Basically, it consists of an Excel sheet with information about, I would say, 1 million songs. And the information are who are the songwriters, or what's the, I don't know if the genre is there, artist name, lyrics of the song. So this is how the data set looks like. It's a very famous data set. Now, here, if you look at, this is the column that is most interesting for us, the lyrics. So lyrics of the song will basically be used for training this Nano GPT so that GPT can learn from scratch how to write songs in English. It won't be very good. The output won't be mind blowing to you because we are only training it for a couple of minutes, but you will still see what kind of output it can produce if we train it on our normal machine. So here, what we first do it is we have this Spotify million song data.csv. So I have downloaded the CSV file from Kaggle, and we'll be using that same CSV file for preparing the training data and validation data. So first, let me run this prepare.py. Don't worry to see this huge code base. There is no intention for us to make you understand any of this code. We just want to show you this process of training a GPT from scratch and then inferring from it. Meaning, right now, when you are calling ChatGPT, when you are uh, giving a prompt in ChatGPT, you are inferring. So the GPT is already trained, as Sahil showed. It took them many weeks and a lot of money to train GPT. So training is done, and now you are inferring from it. So here we will do both. Here we will do training as well as inference. So first, let's prepare the data set by running this code. Now you will see that in this Spotify folder, two more files will form. One will be a train.bin file, I think, and second one will be valid.bin. Yeah. So these two bin files have been created. Basically, it's splitting the data into training and validation set. Now what we will do is we will do the actual training, because now we have prepared the data. Now let's train the GPT on this Spotify million song dataset and see what kind of song GPT can write in 2 minutes of learning. So I have already written the code here, which I can use to run because it's a little bit long. So let me just copy paste this. So when we do the training, it takes 2000 iterations and it takes approximately 3, 4, 5 minutes, depending on your computer, I guess. But you can see that once this starts running, it's not very slow. Like each iteration is relatively fast. So after maybe 50 or 60 iterations, I'll just stop it to see what kind of thing. So right now we have been training it for what, past 20 seconds. So let me stop it. So I interrupted the training at 150 iterations, right? So training was too short-lived. Probably Nano GPT did not get a chance to properly learn from this entire million song data set. Now what I'm going to do is, with this short training, which is highly insufficient, I will just ask. Now we are doing inferencing. So basically, right now what I'm doing here using terminal is exactly what you're doing when you are running ChatGPT. When you run ChatGPT, when you type the prompt, you are asking ChatGPT to create something based on your prompt. Here also exactly that's what I'm doing, and here I'll give the prompt as just a word, sunset. So I want the this Nano GPT to create a song or write a song for me based on this word sunset. And here, if I run, you will see that I hope the font size is visible. I can increase it a little bit. Here you can see that it's creating something, but the output is not very good, especially because there are a lot of words which does not make any sense. See, there is no meaning for these words. I don't know what these words are. So it looks like a song. There are some kind of rhyme and all. I don't even know if there is rhyme, but basically sunset word must be there somewhere. Let's see, where is it? At least at the starting, it should say something about sunset. Okay, here there is sunset. I gave sunset as the cue. Then it's writing something. I don't even know if it's related to sunset. Now let's try to create, and this is another version, I think. Whatever you see after these dots is another version. Here you can see another sunset song lyrics. Here is another one. It makes no sense, but it's writing like how a 3-year-old kid might write. Now let's do one more thing. Let's train this even better. So we realize that, oh, the time we spent is not good enough. Maybe I'm sure at OpenAI, when they were training GPT-3, they would have also encountered the same thing. Maybe they have initially trained for they initially trained for 1 week and realized that their model is very bad. Maybe then they realize they have to train for 10 weeks or 6 weeks. So each training will incur a lot of money. Right now, we don't incur any money because this is a small model. But ideally, you need these NVIDIA GPUs, which cost a lot, and you need tens of thousands of them. And by the way, that's one reason why NVIDIA's stock has risen so much, because Facebook and many other companies, they have purchased a lot of these NVIDIA GPUs. So I will let this training happen for 2000 iterations, and I will show you just because we spent. So here, what is the money here that I'm spending? The only money that I'm spending here is probably the electricity in this room, the electricity that I'm consuming to run this model. Recently, there was a story in US somewhere. There was an Airbnb host, and she suddenly got a bill of $1,500 or $2,000 of electricity just in 2 weeks. And this happened because the guests who were staying in Airbnb that week, in those 2 weeks, they were doing cryptocurrency mining, and they came in with a huge set of this. I assume they will also have needed GPU for computation, and it consumes a lot of electricity. And that these guys found that it's better to rent Airbnb, because that 2 week renting price for Airbnb is much cheaper. They can mine some Bitcoin, and then they can make money off of it. But then whoever was owning that Airbnb has to pay the electricity bill. But while this is wrapping up, let me also show you one more thing. This is a Transformers course that we have released on our website. Just check this out. So this is a live course, live in the sense that it's a living course. It's not a static course. The course content itself is passive, but what we are planning to do here is, you might have noticed that if you guys are following us on our YouTube channel, we have created Transformer from LLM from Scratch series, Transformer series, and we have several lectures which follow this topic. And many students have been asking us if they had one place to go and learn Transformer from scratch with the help of assignments and quiz, so that they can be sure that instead of just watching the video lectures, they can also do something hands-on. That'll be a great thing to have. So this course is basically that place. We are in the process of uploading certain assignments here, so you will get access anytime when you take this course. We recommend you do the following. Once you're confident enough to start looking at, let's say, some assignments, it won't be very difficult, but it won't be very easy as well. You can take this course. Otherwise, you can follow other free material which you will find on YouTube or on our own channel or on other channels. Just check out those things. Once you are ready to kind of learn a little bit more advanced concepts within transformers or large language models in general, you can feel free to enroll in this course. But let's get back to the training. So training is done, right? 2000 iterations are done. Now let's see what kind of output can this Nano GPT produce with same keyword. So I'll give sunset itself as the keyword. So if you guys look at the previous output, it was not English, right? Like many words were very, very bad. I don't know if it is much better right now. I still see many words that doesn't make any sense. Yeah, I don't know what about this is better. Sometimes it's good. Okay, right now it feels, I don't know if I'm biased, but it feels like this is slightly better. Maybe very little bit. I still see many words that have no meaning. But you will. I think there is a little bit of strid. I don't know what is strid. Find. It's probably trying to create some rhyme forcefully. Maybe I don't know. But you can see that sunset is being followed. Sunset are my care to me. What I know to see. I'm gonna bark aft lure. Okay. It's complete gibberish. It's probably the worst large language model in the history of large language models, but still it's something, right? In 2 minutes we created this large language model. We wanted to show this Nano GPT because recently we had conducted a poll. I forgot it was on YouTube or LinkedIn, in which we asked a question: what is the most exciting thing you guys think about small language models? So there is something called small language models, which are much more. It does not have as many parameters. Most of these big large language models are neural networks with 100 billion plus parameters. These small language models have much more smaller order of magnitude parameters. And the most popular answer that we got in our thing or in our poll was people were excited about it because they could run it on their local machine. So that was very interesting because we did not think that would be the most interesting use case for small language model for people. At least I thought people will say, oh, SLMs can maybe reduce costs for companies or something like that. So it looks like most of the individuals, they care about how they can use, how they can train or fine tune these LLMs or SLMs on their own local machine. And Nano GPT is the perfect example of that. So we just wanted to show you a small GPT that you can train yourself and build. SLMs, small language models, are also sometimes possible. You can train it on your own machines. So just check this out. Once you learn the basics of transformers, you can venture into doing these hands-on things, getting your hands dirty yourself. But with that, I think now we can get back to one last section that we wanted to cover today. So you can go ahead, Sahil.
Yeah.
We had planned a 10-minute section for Sahil to go through the last part. But maybe, Sahil, you can just show them the Google Colab notebook and we can share it in the chat because
Maybe, yeah, in the interest of time, since it's already 8:30.
Sure,
yeah.
sure. I'll do that. Okay. Can you see my screen, right?
Yes.
Yes,
Okay.
yes.
Yeah. These are some simple applications of like how just some demos of transformers, and this is the text summarization we can try here on input here. And this is just how we probably use this in code. We probably get it from Hugging Face or somewhere where the models are hosted, and then you just take it from there. And even there are vision transformers you want to try out. Yeah, this would help you capture an image. And this is not a convolutional neural network, mind you, because this is a vision transformer entirely. And a vision transformer is something which is slightly different. But what it does is instead of text input, it just takes image chunks as input. Yes, you can try this out yourself since we don't have time for me to show this demo, but it's pretty direct. You can just try to run this. And the first part is just a next word prediction with GPT-2. And let me just try the same thing here, see what the output comes. If, like, okay. I think it might take a bit. I think you can try all of these by yourself. And there are even more models which are available on Hugging Face where you can directly get it. I think it's just loading up the model. Just give it a second. Yeah, it just predicted this token one with this probability, and that's the highest probability, just a call with 0.9. So of course, it's varied depending on the model weights and how it is trained, what data it is used at. You can try this out. I've shared the collab notebook on the chat. Yep, that's all. Okay.
Okay, I think we are just past time. So thanks a lot everyone for joining. Before actually leaving, can we take a group screenshot? We have made this a tradition now. So everyone, if you can just turn on your webcam, we can just do something like this and take a screenshot. All of you have been very interactive throughout this session. So I guess we'll need to enable some permissions for webcam, right?
I just did.
Okay. So great. Don't be shy. Just enable your webcam and we'll just take a photos like a screenshot. Okay. So you can do something like this or this. Okay, I'm taking a screenshot now. Okay. Thanks everyone. We'll be conducting more sessions like these this month and next month also. Hope you enjoyed this series on LLMs and transformers.
Thank you, everyone. We'll meet
Thank
again
you.
in a couple of weeks, hopefully. See you all. Bye.